Okay, geometry students, this is your Unit 2 review. This unit encompassed pretty much entirely transformations and symmetry, and that also dealt with midpoints and distances and slopes and equations of lines and things of that nature. Okay, so let's take a look. As we discussed, there is a broad category that covers the different types of transformations. Okay, so a transformation takes an object, which is referred to as a preimage, and it alters it in some way. After this alteration has occurred, we don't have a preimage anymore, we have an image. And as you already knew from your days in junior high, there are four basic types of transformations. They would be reflection, rotation, translation, and dilation. Now, three of these transformations are referred to as isometric, meaning there is no change in the size of the object. Reflection would be one of the isometric transformations, and reflection, strictly speaking, bounces an image through a plane. And we talked about doing reflections, and there is a little bit of a tendency towards people messing up reflections, and it's not because they're so terribly difficult, it's just because we get in too big of a hurry and it causes us to make silly mistakes, especially if our mirror, our plane of reflection, is not perfectly vertical or perfectly horizontal. We have a habit of trying to translate through the mirror rather than reflect. So I gave you a fail-safe way to try to remember or never ever miss a reflection, and that is to think of your object as a collection of points rather than a complete object. So this capital D in this particular case, if we wanted to reflect capital D through the mirror, then you take it one point at a time and you simply ask yourself, okay, when that point, this corner point, looks into the mirror, it will see itself the same distance out behind the mirror. Okay, and if you do this repeatedly with the different points, moving them one at a time, okay, then what you end up with is a reconstructed figure on the opposite side of the plane of reflection, and you connect your dots and you have it done. Like I said, it's not that big of a deal if your mirror is perfectly vertical like this one or perfectly horizontal like being underneath the D or something like that, but a diagonal mirror, it's actually very difficult to envision what the final product is going to look like, but if you move it one point at a time, pretty much guaranteed you never miss it. Okay, we also talked about rotations. Obviously, a rotation rotates a figure around a given point. So there's a couple pieces of information that you're going to need to know in order to do a rotation. First off, we need to know what we're rotating around. There has to be some anchored point in our diagram, and then we need to know how far this rotation is going to travel. So typically rotations are given in terms of fractions of circles, and we know well that there are 360 degrees in a circle. So typically you get rotations like 90 degrees, 180 degrees, 270 degrees, which are basically quarter turns of a circle. And then you need to know the difference between the two directions. Clockwise is as you start at the top of a circle, traveling around to the right. Counterclockwise is starting from the top of a circle, would be traveling around to the left. Okay, and also gave you foolproof way to ever miss a reflection or rotation, pardon me. Okay, and that is to pin your point of reference basically to your desk. Okay, so like using your pencil, basically pin the point down to the desk, and then actually physically rotate your paper the direction and the amount that you're told to. So in this case, rotate 90 degrees clockwise around the given point. Okay, so we're going around to the right side, and if we rotate 90 degrees, which is 1/4 of a circular turn, then basically you are currently looking at what your final product should look like. A capital A with its peak pointing to the right, and then the reference point down below that. So all you have to do is basically recreate exactly what you're looking at this moment, and you have your rotation. Translation, pretty easy. Translation simply relocates the object, so it's basically just moving it. Your junior high teachers called it a slide or a glide. That is incorrect vocabulary. Okay, that brings us to the dilation. Dilation is the only type of transformation that is not an isometry, okay, which means our resulting figure is not going to be the same size as our beginning figure. The image is going to be a different size than the pre-image was. And how do we know how much the figure is going to change size or whether it's going to get bigger or smaller? Well, that is controlled by a scale factor. Scale factor is a ratio that tells us how much a figure enlarges or reduces. Okay, a thing to remember about reading scale factor is it is always read, if it's in the colon notation like you're seeing on the screen now, it is read left to right, and that would be your pre-image to your image. So when they say a scale factor of 1 to 2, they are saying your pre-image is size 1, your image is size 2. So basically your image is going to double in size from your pre-image. Okay, if they happen to put it in fractional form rather than colon form, then you read it downward, just like you would a regular fraction. Numerator, then denominator. Your numerator is your pre-image, your denominator is your image. Okay. We also talked about different types of symmetry. Okay, there are 3 different types of symmetry. There is reflectional, and of course reflectional is the ability of a figure to be exactly the same on either side of a line. So basically, is there a location where you could put a mirror right through your figure, and looking into the mirror would be exactly the same as looking at the shape itself. Okay, so you got, like in the case of the arrow, the left side is exactly the same as the right side. Okay, and it doesn't have to be left and right. It can be top and bottom. It can be diagonal. It can be all kinds of different things. Okay, and obviously objects may not have any reflectional symmetry at all. On the other hand, they might have a single line of symmetry like the arrow. They might have several lines of symmetry like the hexagon, or they might not have any symmetry at all like the parallelogram on the right. Okay, rotational symmetry is the idea that you can take a figure and begin to spin it in such a way that it will realign with itself before completing an entire revolution. So by obviously turning this quadrilateral, we can see that 90 degrees worth of a rotation makes it look exactly like the pre-image did, as if it hadn't been disturbed at all. So this figure has partial rotational symmetry. It does not have total rotational symmetry. As you can see, if we stop rotating it right there, clearly the figures do not realign. So the only type figures that have total rotational symmetry are completely circular objects. Okay, translational symmetry, a little bit harder to come by because you must have a recurring pattern inside of your object in order for them to realign. So the same idea, the idea that you could take an image of a figure and reposition it with the figure itself, and you cannot see the difference between where the image is and where the pre-image is. And obviously this pattern, there is a pattern in here, and you have translational symmetry. The next thing we did is we started playing around with graphs a little bit for the very first time, and the first one we took a look at was the midpoint formula. Now the midpoint formula is not anything new to you. You've done it in Algebra 1. Okay, and the midpoint obviously is the idea that there is a location that is exactly in the center between 2 other locations. And if you get to thinking about it, this is really a very simple formula, because somewhere in between the x values of your 2 points, there must be an x value that's exactly in the middle. Well, exactly in the middle is like an average. Same thing with the y's. Okay, the 2 points that you have y values. There must be a location that is exactly in the middle between those 2 y values. That is like an average. So another way of thinking of the midpoint formula is to think of it as a coordinate that is found by taking the average of the x's, comma, the average of the y's, and then putting them in there with the parentheses and of course the comma, and that'll tell you exactly where your midpoint is. Okay, so the one thing I had you do, and I made you do it repeatedly, some of you ended up hating me for it, okay, but I forced you to label your points. Okay, the formula is not difficult, and the math in the formula is not difficult, which means the difficulty arises with us not plugging information in the correct places. The 2 points that you have in your midpoint problem, they have locations. We are going to call them point 1, which lives at x1, y1, and point 2, which lives at x2, y2. And I had you actually label your points, and I had you actually write down your formula each time you needed it. Then it was simply a matter of connect the dots, just plugging numbers into the formula where they belong. And since you have it all labeled, it's virtually impossible to plug in the wrong place. And then you simplify your numerators and then divide your denominators. Okay, and you ended up with your midpoints. Okay, so no big deal there. The only real catch that came across with midpoint was a new idea that instead of using the midpoint to say, hey, here are two end points of a line segment, let's find the center between them, questions have more recently been asking us, hey, here is an end point and here is a midpoint. Where is the other end point? And we actually applied what became kind of known as a smaller version or idea of slope, is that in order to get from your end point to your midpoint, your x value had to change a certain amount and your y value had to change a certain amount as well. Well, if the x value had to change a certain amount and the y value had to change a certain amount to get from the end point to the midpoint, since the midpoint's exactly in the middle, it must have to change the exact same amounts to get from the midpoint to the other end point. So that's kind of what we did. We figured out how does the x change from the end point to the midpoint, and then made the x change the same amount again, getting from the midpoint to the other end point. Same thing with the y's. To get from one end point to the midpoint, y had to change a certain amount. Let's force it to change the same amount again, and that'll get us from our midpoint to our other end point. The second thing that we did when we were given 2 points is we learned to find out how far those points were apart from each other in the graph. And to do that, we employed the distance formula. Now, some of you are still under the very bad impression that if you want to know how far 2 points are apart in a graph, that all you have to do is kind of count the grid lines that you bump into as you travel along the line segment from one endpoint to the other. And that is unfortunately a horrible thing that some junior high teachers are out there teaching you. It's just not good. It's not accurate. It does not work out. But we do have a very precise formula that'll tell us exactly the location between 2 points. So once again, given 2 points, we will label our points. Point 1 lives at x1, y1. Point 2 lives at x2, y2. And then we have this big nasty formula, the square root of the difference of the x's squared plus the difference of the y's squared. And all we have to do is plug in our points, okay, into the formula after everything is labeled and you have your formula written down. Again, it's just kind of connect the dots. Very difficult to actually plug in incorrectly, and you should be able to get all the way down to an answer, simplifying the stuff that's inside of the radical, following your order of operations. Then we also learned to simplify those radicals manually, just in case we ever need that skill. Okay, but in most cases we were able to use our calculator on a test and go and find an answer that way. Okay, so not really much difficult to deal with the distance formula. The third thing that we learned how to do with 2 points was when we had 2 points and a line connecting them, then that line had a slope value. So we spent good amount of time talking about lines and one of their properties, which is slope. Now, a line basically needs 2 things in order to do what it does. It needs somewhere to begin and it needs somewhere to go. Okay, somewhere to begin is very easy. That's the y-intercept, and we'll come back to that here in a little while. It's the slope that requires some calculation. Okay, so basically what we need to know is if we travel from one point in a graph to another point, how much does the x value change? How much does the y value change? And that, in a word, is slope. We talked about there's a lot of synonyms to deal with slope, a lot of different ways that they can refer to slope in a problem, and we needed to be familiar with all of them. Clearly, they could use the word slope. Clearly, they could use the algebraic variable m, because that's what it represents in slope-intercept form. Y equals m, x plus b. M is for the slope. Junior high, they said rise over run a good bit, but you're going to see see that fading away. The formula for slope is y2 minus y1 over x2 minus x1. That is actually how we calculate the slope value, the difference of the y's in the numerator over the difference of the x's in the denominator, rise over run. That tells us how the line travels from one point to another. So it is possible they might refer to slope by the formula itself. In written form, the formula is pronounced change in y over change in x. So it's possible they might use that English language on us. In more scientific language, we might see something like delta. The little triangle that you see there is the Greek letter delta. Delta means change. So when you read this little fraction on number 6, we see the change in y over the change in x, which is exactly what number 5 says and exactly what number 4 says. And we talked about this one. The current favorite vocabulary for word problems seems to be the term rate of change. If you hear a problem refer to rate of change, they are talking about slope. Okay, now we saw several things that slope can do. Obviously, slope could be a positive fraction. It could be a negative fraction. That is the difference between a positive rise, meaning the graph is moving upward as you read from left to right, or a negative value means a negative rise, meaning the graph is falling as you read from left to right. Okay, 1 is kind of like the reference point for slope. So if you have a slope of 1, that's kind of considered the normal speed of the graph. Okay, however, as slope values get to be larger than 1, like 1.5, 2, 3.5, 5, 6 and 9/17, stuff like that, your graph is rising faster than it is running. That's going to cause the graph to look more steep inside of the Cartesian coordinate plane. On the other hand, if your graph gets smaller than 1, like 3/4 or 1/2 or 1/6, things like that, that means your graph is running faster than it is rising. So that's going to cause the graph to lay down more when you see it in the Cartesian coordinate plane. Okay, a couple of special cases here. A horizontal line we say has zero slope, and it has zero slope because it is refusing to rise. That puts a 0 in the numerator of our slope fraction, and we should know by now that 0 for the numerator of a fraction results in a value of 0. That's why they call it zero slope. However, a vertical line is refusing to run. That puts a 0 in the denominator of a fraction, and that is a big no-no to have your denominator equal 0. That's what we call infinity or undefined slope. Okay, so we did some examples on how to actually calculate the slope, and once again, we need 2 points. We're going to label them, point 1 at x1, y1, point 2 at x2, y2. We will write down our formulas, we will plug in, we will reduce, and we will have our slope. Now, from the slope value that you get, you ought to be able to understand positive 1/2. That is a slope that is moving upwards from left to right because it is positive, and it is a slope that is more horizontal than vertical because the denominator, the run, is larger than the rise. Okay, so we worked out some additional examples, and that was it for slope. Now that we knew how to deal with slope, it came time to say, okay, well, what happens if we know the slope or can calculate the slope but do not know the y-intercept? Because both of those values are going to be needed to know. We're going to need to know those in order to assemble the equation of the lines. Of course, the slope-intercept form, the basic format for equations of lines, is y equals mx plus b. M represents the slope, b represents the y-intercept. We've already talked about calculating the slope part of the equation. Okay, now it's about the y-intercept. And so a couple of special cases that deal with equations of lines. These guys don't really fit the true nature of the slope-intercept form. If you have a horizontal line like you're seeing at the top, well, we already said that the horizontal line has 0 slope. So in slope-intercept form, that means we have y equals 0x. Well, if there are no x's, then we are not even going to write the x's down. So you will simply have an equation that says y equals, and then your b value. Where does it cross the y-axis? In this case, it crosses at -4, so y equals -4. The vertical line is kind of a different animal altogether, because in order to be vertical, we already said that it has to have a slope value of undefined. Well, how do you plug an undefined value into an equation without destroying the equation? The answer is you can't. So the slope-intercept form actually will not apply when we are talking about a horizontal line. But just like a vertical line had an equation that said y equals wherever it crosses the y-axis, now we have a line that only crosses the x-axis. So its equation will say x equals wherever it crosses the x-axis. In this case, positive 3, x equals 3. Okay, now a lot of the equation writing stuff is very simple, especially if you are handed the y-intercept. We can calculate the slope really with no problem. The question arises, or the problem arises, when you get to the what happens if they do not give you the slope value, and you end up sitting in a spot like that where you have the slope but the y-intercept is unknown. Well, you're not out of options yet, because the basic rule for all of graphing is if you know of a point that does in fact live on a particular graph, in this case a line. Okay, if you know that you have a point that lives on that graph, then you can take the coordinates of that point and you can plug them into the equation. That is absolutely a fair thing to do with a problem. Well, we know typically with lines 2 points that are on our line. We can take any of those points, the x comma y, but you got to get x and y from the same point. Do not get x from one point and y from the other point and then plug them in. That won't work. Okay, but take your x comma y from one of your points and plug them in for x and y. And as you can see, when you plug in there, you will have only one variable left, and that variable will be your b. Then you follow your 5 steps. Your parents' complaints vary for everyone, and you solve for b. That gives you your y-intercept. Then when you plug in your b, you're good to go with your equation. Okay, so the rest of this was more practice on that same skill. A little bit more information on slopes of parallel and perpendicular lines, couple little tidbits. Okay, if two lines are going to behave in a graph such that they are parallel to each other, meaning they will never intersect in the same plane, and then you have two that are possibly perpendicular, meaning that they absolutely do intersect in the same plane, and they form a right angle at the intersection, there must be something about their behavior. And as we've already discussed, their behavior is controlled by the slope value. So there must be something about the slopes that causes that to happen. In fact, there's very specific stuff. If two lines want to never intersect in the same graph, that means they must be running and rising at exactly the same speeds. Because if that weren't true, eventually they would hit each other. So if they're running and rising at exactly the same speeds, that means their slopes are equal. So the only way for two lines to be parallel in a graph is for their slopes to equal each other. If they want to intersect, well, all they have to do is have different slopes. But if they want to intersect and form a right angle at that intersection, so they will be perpendicular, then their slopes must be negative reciprocals of each other. And that means take one of the slope values, examine it, and go, okay, if I took this slope value and I changed its sign and turned it upside down, would that make it look exactly like the other slope value? If it does, then congratulations, you have perpendicular lines. If by changing the sign and turning it upside down, it does not match that other slope, well, you have two lines that are going to hit, but they are not going to form a right angle at that intersection. I believe the rest of this was just demonstrating that point. And if all of that wasn't enough information already, we also had to deal with the four translations or four transformations in the Cartesian coordinate plane. So basically the idea of reflections, rotations, translations, and dilations happening in a graph. Okay, so we went through those one at a time. Okay, and the very first bit of information we have here is a little vocabulary on the idea of an ordered pair. Okay, now an ordered pair is actually broken down into a couple of really technical terms for the x and the y values. Okay, in mathematics, the x value is actually referred to as an abscissa, that is the x part of an ordered pair, and the ordinate, that is the y part of the ordered pair. Okay, now all of the transformation information deals with how do the abscissa and the ordinate change in the different transformations. Okay, so obviously you have your image and your pre-image, okay, or actually your pre-image and then your image, and we discussed that after a transformation has happened, obviously you go from a pre-image to an image, but the labeling inside of a graph, you start to pick up what they call prime markers. Okay, so quadrilateral A, B, C, D, after it has been transformed, is now A prime, B prime, C prime, and D prime, and it can be further transformed. A prime, B prime, C prime, D prime could become A double prime, and then B double prime, C double prime, D double prime, and this can go on as long as is needed. Okay. Now, dealing with translations are really very easy because everything moves at the same speed with a translation. All we need to know is how far to move it. Okay, so if in this particular case you're told to move, a figure 6 units to the right, then it's simply a matter of relocating everything 6 units to the right. You connect the dots and you've got your new graph. It's not a big deal at all. So a lot of times what you'll see when translations are involved, either there will be another transformation going on simultaneously, or perhaps they will cause you to move more than one direction in the graph at once. Like this says, if you're moving it so that a particular point is on the origin, well, B can't get there just by moving one direction or the other. It has to move two different directions to get that done. You may have to identify that and then apply the same speed in order to get that done. Okay, reflections, a little bit more difficult, but still pretty straightforward. Okay, reflection is quite simple in the idea, the same idea that we started off the unit with, that each point is going to look into that reflecting plane and it's going to see itself the same distance out behind the plane. So in this case, this problem wanted us to reflect through the y-axis. We're just going to take it one point at a time and go, okay, each point's going to look into the mirror and it should see its image the same distance out behind the mirror. Okay, so when you apply that same idea, it's very easy to reconstruct the figure and then you can get your points from there. If it happens to be, let me get past this for a second. Okay, here's that dreaded slanted reflecting plane that we were talking about. Okay, and the plane of choice is typically the parent linear function y equals x. And there's a very simple thing that goes along with reflecting through the line y equals x or y equals negative x, is the abscissa and the ordinate for each one of your ordered pairs. They are going to switch places and switch directions. Okay, so that's really not a big deal. So all you have to really do is identify your ordered pairs, and then you reverse your coordinates values. You can see there at the bottom of the screen, the abscissa and the ordinate have been flip-flopped. Then you can plot your points, and no big deal to connect the dots. Okay, the last of the isometric transformations was the rotation. A little bit harder to deal with, but still not too terribly bad. You just need to learn a couple of things. Okay, so getting past the basics there. Rotations, typically what's going to happen with rotations is you're going to be moving either the entire object or at least parts of the object in and out of different quadrants. So it's important to understand which quadrant is which and what the signs are doing in those quadrants. Now, of course, the top right quadrant is quadrant 1. That is where everything is positive. And then the quadrants naming system rotates counterclockwise from there. So top left is quadrant 2. That is where the x's are negative, but the y's remain positive. And then the next one's quadrant 3. That's where everything is negative. And the next one is quadrant 4. And that's where the x's are positive and the y's are negative. Okay. Now, for the 90-degree rotation, no matter which direction you go, whether it be clockwise or counterclockwise, your abscissa and your ordinate are going to switch places. Okay, however, you need to pay attention on which quadrant you are moving into in order to get the signs for your abscissa and your ordinate correct. With 180-degree rotation, okay, you are going to have the abscissa and the ordinate stay basically in the same place. So the values will remain. But again, you're going to end up in a different quadrant. So whichever quadrant you end up in after that rotation, you need to pay attention to the signs there and adjust those. Okay, so it was pretty straightforward as far as that's concerned, and you can go back and look at the video if you need to see that work, but you've got the basics: 90-degree rotation, the abscissa and the ordinate swap, watch out on your signs, and then on 180-degree rotation, the abscissa and the ordinate stay the same, and watch out on your signs. Now the dilations is the tricky one. Okay, dilations in the coordinate plane. This is a little bit trickier because typically there are more than one transformation going on at once, and usually it's a dilation and a translation of some kind. Okay, so here we go. There's a lot of different ways to think about it. A lot of times the idea of midpoint can apply, the idea of distance can apply, and the idea of slope is a huge factor when it comes to dilating. Okay, so they're going to have to tell us how much they want us to dilate. So typically they're going to have to provide us with a scale factor or enough information that we can figure out the scale factor for ourselves. And then they'll have to tell us what we are dilating towards. And a very popular way for them to do this is to say, hey, we're going to dilate into the origin. So basically the idea that this triangle is all three of its corner points are going to get closer and closer and closer together as it approaches the origin, until ultimately all 3 points are piled on top of each other at the origin, and it ceases to be a triangle anymore at all. Okay, so like in this case, it tells you to dilate the triangle with a scale factor of 2 to 1. Well, 2 to 1, of course, means that it's getting smaller. Since the ratio is getting smaller as you read it from left to right, 2 becomes a 1. And that also tells us that it's getting smaller by half its original size. So one of the things that we can do is we can figure out the lengths of all 3 of these sides and figure out how much half of those lengths would be. That would be one way to do it. We can go from each of these corner points, A, B, and C, to the origin, and we can find out what the midpoint between the corner points, the vertices, and the origin would be. That would give us a figure that's exactly half as big. Or we can apply the idea of slope. As you get from A to B, how much do you have to rise and run? And then take half of those values and only rise and run half as much, and that will show you kind of where you're at. Okay, so one of the easiest first steps to do is, if you know the where you're going to converge into, what is the point of dilation? Okay, you can kind of just sketch yourself a few lines, and of course your points are going to have to be on there somewhere. And then whether you're using distance or midpoint or slope, it should be fairly easy to figure out where those points have to be positioned on these lines. Okay, so in the notes I gave you, I did look at slope, so we kind of figured out how much a figure sloped from one point to another, and in this case, since we wanted half, we took half of the slope, and that kind of told us where the points needed to be in between the points and the origin. Okay, so you can look back at that those notes if you're still having trouble with that. And anyway, that is a ton of information that was in Unit 2. We actually spent several class days looking at some activities on the wall and stuff like that. So a lot of information in Unit 2. So if you have forgotten Unit 2, this is probably a real good one to refresh your memory on.